Question number 7. The curve C has the equation y is equal to x squared plus x plus 9 all over x plus 1. So on A, find the equations of the asymptotes of C. Alright, so here we're going to start with the vertical asymptote. And for the vertical asymptote, we find it when the denominator x plus 1 is equal to 0. So the equation of the asymptote here is x is equal to minus 1. So that's the vertical asymptote. And then for the oblique asymptote, we're saying we are going to divide, since we have y is equal to x squared plus x plus 9, and it's all over x plus 1. Then if we divide x plus 1 into x squared plus x plus 9 and we get the quotient, that'll help us get the equation of the oblique asymptote. So you can do long division, or even by inspection, you can notice that we can express or factorize x squared plus x by factoring x out. So that's x bracket x plus 1 and it's plus 9. And that's all over x plus 1. And this is the same as x of x plus 1 all divided by x plus 1, and that's plus 9, and that's over x plus 1. Alright, so you can notice that we can cancel out the x plus 1s here, and we're left with x plus 9 over x plus 1. So that's y is equal to x plus 9 over x plus 1. So the quotient here is x, and with the quotient we can come out with the equation of the oblique asymptote. So the equation of the oblique asymptote is y is equal to x. So we now have the two equations, one for the vertical asymptote and the other one for the oblique asymptote. Let's go on to part B. On part B, it goes, find the coordinates of the stationary points on C. Now I'm going to take the equation of the curve C. So here it is. So this is the equation of C, and I'm going to find dy by dx. Okay, so I'm going to use the quotient rule, where I'll take the numerator to be u and the denominator to be v. So using the quotient rule, I have my u being equal to x squared plus x plus 9, and therefore the derivative of u is 2x plus 1. And then I have v to be x plus 1. So the derivative is 1. So I'll then say, therefore dy by dx is equal to vu prime, which is x plus 1 multiplying 2x plus 1. And that's minus uv prime, which is x squared plus x plus 9 multiplying 1, and it's all over v squared, which is x plus 1 squared. So we can simplify here. Simplifying the numerator, the two brackets here gives us 2x squared plus 3x plus 1, and that's minus x squared minus x minus 9, and it's all over x plus 1 squared. So that's 2x squared minus x squared is x squared, and 3x minus x, that's 2x, and 1 minus 9 is minus 8, and that's all over the denominator, x plus 1 squared. So this is the expression for dy by dx. Now, since it's a stationary point, we know that at stationary point, dy by dx is equal to 0. So therefore, we are going to equate this expression to 0. And if we do, we will multiply both sides by x squared plus x plus 1 squared. And we will eventually get x squared plus 2x minus 8 being equal to 0. Now, by factorization, we have x here and we have x here. We should have 4 and 2, and this should be plus and this should be minus. So therefore, the values of x are minus 4 and 2. Now, we also need to know what the corresponding y values are. It means that we will need to substitute minus 4 into the equation here of y. And if we do, we'll eventually get the coordinates of stationary points to be, when x is equal to minus 4, y should come out as minus 7. So that's minus 4 and minus 7. And if x is equal to 2, substituting into the equation here of y, we get the value of y to be 5. So that's 2, 5. So these two are the coordinates of the stationary points. Let's move on to part C. On part C, the question goes, sketch C stating the coordinates of any intersections with the axis. Alright, so what we're going to do here is to make a sketch. So I have my axis. So this here is y and x. And I'll start with the two asymptotes. So the first asymptote is x is equal to minus 1, and the other one is y is equal to x. So let's start with x is equal to minus 1. That's the first asymptote. So it intercepts at minus 1 here. And then we have the oblique asymptote right here. And now my graph will come out like this. I have to consider the fact that we've got two stationary points, and that's at minus 4 and minus 7 and 2, 5. So I know that my graph is gonna be coming out like this. So there's an intercept here on the y-axis, and to get the y-intercept, I'll take the equation and say for the y-intercept, x is equal to 0. And when x is equal to 0, y substituting 0 here, we get y being 9 over 1, which is 9. So the coordinates here are 0, 9. We are going to plot out the other part of the graph, which has a maximum stationary point, and here it is. Alright, so now we have the graph, and we can scroll down to part D. So on part D, it goes, sketch the curve with the equation y is equal to mod x squared plus x plus 9 over x plus 1, and find the set of values of x for which 2 of mod x squared plus x plus 9 is greater than 13 mod x plus 1. Alright, so this is a modulus graph. So this means that I'm going to reflect the part of the graph that is below the x-axis, above the x-axis. Alright, so if I am going to do that, it should come out like this. So the asymptote is reflected this way. So we managed to reflect the part that was below the x-axis above the x-axis. So this is what we now have. So now that we have the modulus graph, we also want to answer the part that goes, find the set of values of x for which 2 mod x squared plus x plus 9 is greater than 13 mod x plus 1. Okay, so how are we going to do that? If I take this equation and I divide both sides by 2 of mod x plus 1, then I see that I can cancel this, and be left on the right side with 13 over 2. And on the left side, I can cancel out the 2's, and I'm left with x squared plus x plus 9, and it's over x plus 1, and it's all under modulus. So if you look at this modulus expression, that's the same as the one that we have for the curve. So here we're considering y is greater than 13 over 2, which means that I'm going to go on the graph and I'll draw the line y is equal to 13 over 2, which is 6.5. So it should be somewhere around about here. So this is the line y is equal to 13 over 2, which is as good as 6.5 as a decimal. So this is the line here. So we have two critical points in which one is here and the other one is right here. So I'm going to say for the intersection of this part of the curve and the line y is equal to 6.5, I'm going to solve x squared plus x plus 9 over x plus 1 being equal to 13 over 2. So if I cross multiply, then I'll get 2 of x squared plus x plus 9 is equal to 13 of x plus 1. So that's 2x squared plus 2x plus 18 is equal to 13x plus 13. So that's 2x squared, and that's minus 11x, and then that's plus 5 is equal to 0. So factorizing, we will get 2x here and x here, then minus 1 and minus 5 here. So that's all equal to 0, and therefore the values of x from this we get to be a half and 5. So this means that this is a half and this is 5. Now we want values of x that satisfy this inequality here, where the graph of y, that's the modulus graph, is greater than or above that of 6.5. All right, so we will take values of x, that's for the solution. We'll take values of x that are less than a half. That is where, if you look at this value here, you can notice that for values that are less than a half, values of x that are less than a half, the graph of the modulus is always greater or above that of y is equal to 6.5. And we also have values of x that are greater than 5, where the graph of modulus is also above that of y is equal to 6.5. So that's x greater than 5. So this becomes our solution set. That's the answer right here.